So last time we talked about polynomial regression, and we gave some examples of made-up data, but I wanted to give you a concrete example. So let's go to CoCalc, and I think it's under slides. On slides, I've been really loading up Z-space. I've probably got too much stuff in Z-space now. But let's look at concrete example. So this is a little bit of a pun. We're using a data set that actually is about concrete, about the compressive strength of concrete. And here's a link to it. You can get it off the UCI machine learning repository. So here's what the columns are. So you have just a description of different types of cement. So you have different types of concrete. So there's a certain amount of cement, and then how much. These are the components that go into it, like water and other things. And then there's the age, and in the very last column is the concrete compressive strength. So that's how strong the concrete is. And I picked, I was actually just Googling around looking for some data set that related to strength, because we're looking for nonlinear relationships. So, things that have to do with strength are often nonlinear. Like, at what point in your life do you have your maximum grip strength? You're weak when you're a baby and when you're old. And concrete, similarly, is, it takes a while to age and things like that. Okay, so if you look at some of this data, let me just run all about. It's nice for us maybe just to look at some data sets that come out in real life. So what I'm doing here is I'm doing a scatter plot of the -1 column is the target, and then the 7th column I think is age. But if you want to see a different plot, you can change this number to like 5 or something. And so this is kind of interesting. You see like no clear correlation between any particular variable and the target. And that's often true. And often people that aren't experienced in machine learning, like scientists, what they want is like the unidimensional solution. They want to know like, well, which component is it that relates to strength? And it's not that strength is a function of any particular feature from this data set. It's all of them in aggregate. And that's for two reasons. One reason is that there might be a multi-dimensional relationship between several columns that you just can't see in these low-dimensional projections. And another reason is that each column has noise, but they are kind of independently noisy. So when you come up with a model that combines different columns, it can be that the noise cancels out. And so you need like the noise canceling aspect of combining all these different features plus the multi-dimensional relationships. Okay, so here we just do scaling and train test split converted into a NumPy array. Here's the scalar transform, and here's the test train split. Now we do polynomial features. So I did a degree 2 polynomial, but remember this can be kind of combinatorially explosive. Last time I didn't know the formula, and I had a vague memory of it being in the book. The formula for a degree 2 transformation is in the book, and you can look it up. It's basically the square. It's approximately the square of the number of features. Maybe it's like let's. I should have had the page bookmarked, but it's like the number of features times the number of features minus 3 divided by 2 or something like that. See if that actually works. So there are 7 features here, right? 1, 2, 3, 4, 5, 6, 7, 8. Oh, there are 8 features. So if I do 88 divided by 2, yeah, that's right. 88 divided by 2 plus 1 for the bias column. So the formula here for the number of columns you get after the multivariate transformation is D, the number of columns, times D plus 3 divided by 2. And you know, you could prove that through induction or something if you are experienced in writing mathematical proofs. So now it has the same number of rows as before because we haven't changed the number of data points, but we have changed the number of columns. So we've added a column for the square of every feature, and we've added columns for the product of every two pairs of features. Okay. All right. So here's the performance of the polynomial model in terms of R2 score. So here, this first number is how it does on the training set, and the second number is how it does on the test set. So remember, with R2, it's better to be close to 1. So it does better on the training set than on the test set. And that's generally what happens, you know, because that's what overtraining is. So every model will overtrain a little bit and do a little bit better on the training set than it really does on unseen examples. So it's R2. The closer to 1 you are, the better. And here's what it looks like without the transformation. So if you just do plain old linear regression, you get an R2 score of about 0.4. But if you do the polynomial transformation, then even on the test set, it goes up to like 0.7, which is a huge improvement. And then I just got curious, and Anna actually mentioned this in class one time. She mentioned the random forest regressor. So this is a good model. So and the library implementation from sklearn is very smart. So it's probably making a lot of good parameter choices and things like that. So how well does sort of like a really thoughtfully constructed model do? It gets all the way up to 0.91. I find that just amazing when you look at these scatter plots that seem to show no relationship, that the information really is there. It just is not accessible to a human being, but these machine learning algorithms can figure out the relationships. So I also put a copy of this in your activities folder, and you're invited to sort of change the number of features here. But let's just make a prediction. What if I put this up to 4 based on what we talked about last time? What is going to happen to the training error and the test error, do you think? Just in terms of up or down.
Possible that it's going to get overtraining because the data is doubled, or the
Yeah,
doubled.
right. So the matrix is going to get wider, but it's going to have the same height. So you're gonna do a little overtraining, like Yuri said. So this is going to bring the training error down, but it's going to be overtrained or overfit. So it's going to, yeah. So the test error should go up. So let's run all and see if that actually happens.
So professor, so the variance will go up as well, right?
That's right. The bias is going way down, but the variance is going way up. Mm-hmm. And so here you can see the training error now is almost, it performs almost perfectly on the training set, but the performance on the test set has gone down because now it has more degrees of freedom and it's overfitting the training set. So you can go through and find like the optimal level of complexity for this model. And I think it turns out to just be 2. I think 2 does the best. I guess we can try 3 also and see what happens.
What if we try like 2.5?
Oh, look, 3 did better. You can't, it has to be a discrete number because a polynomial is like a discrete object. So you either, you know what I mean?
Yes.
So there's a certain number of terms, and there can't be a fractional number of terms. So this, I didn't expect that. I think when I was doing it earlier, it's maybe it has to do with the test train split or something. Could do this a couple times. No, it seems like degree 3 is actually better. So that's the sweet spot here for this particular data set. Notice that it's still overfitting, but the point here is that the test score is going up. So here I'm fiddling around trying to fix this number. This is an example of something we call a hyperparameter. It's not like it's not something that gets tuned when you do when you find the optimal W. It's sort of like a meta feature of the algorithm. And often when you tune these hyperparameters, you can work the test set kind of hard, because I'm using the test set here to tune this number to the number that gives me the best performance on the test set. But as I do that, I could be overfitting is coming into play again now, because now the test set is not really independent of the model anymore, because I have selected this number just to please the test set. So this is still useful in selecting the optimal value of the hyperparameter. So 3 really is the best one. But if I fiddle around with this too much, this will no longer be a good predictor of out-of-sample error. So I can still use it to select, to do model selection, to select the best model, pick this number to be the best. But as I futz with it and try different values, this will become optimistic as a measure of the out-of-sample error. So you just have to be aware of that. And often people will keep a third set of data in reserve called the validation set. So after you have, after you've used one data set that's been reserved to train the hyperparameters, you then use a second set of reserved data to evaluate the out-of-sample error. You don't always have enough data to do that, but it's good to do it if you can. Then you get the,
just
yeah.
a quick question. So like to decrease the bias problems, then you can try decreasing the lambda, right?
Yeah, that has to do with regularization. And I do have my regularization lecture queued up here, if I didn't destroy it earlier. We're gonna go through bias and variance, and then regularization is next. So we're just introducing like bias and variance now, and then we're going to talk about ways to control them. And the main way that you control them is using a trick called regularization, and that has a hyperparameter, sometimes called lambda. Our book calls it lambda, which Anna is referring to, and you tune that to optimize the bias variance trade-off. Are you guys looking at my CoCalc right now?
No.
Oh, you're looking at the
Note.
other thing. Okay. Okay, good. Is this, now you're looking at CoCalc?
Yes.
Sorry, I'm just gonna stop sharing because I'm not sure what you guys are seeing. Okay, now we're gonna look at other slides. You guys have copies of these also. Okay, now I see the green box. That makes me happy. So we'll go back to Z-space, and here's something that the books don't talk about. This is kind of like a lowbrow thing, but it comes up a lot in real data sets. Like when I had my students do their final projects last time I taught this course, everybody picks their own data set, and then people had a lot of problems with like nominal data in their data sets. So we've been talking about data where every column is just numerical. So it's just, these are all floating point numbers. But sometimes you'll encounter data. A lot of data sets have columns that are not numbers. They're names, or one of a small number of integers, or like it's discrete. It's just a small set of distinct possibilities, like this sex column in this data set, which is either male or female or immature. So this is about Abalone, which is some kind of mollusk. I've never seen one. Anybody ever seen an abalone? Should we Google one real fast just to see what one looks like? Here we are. So it looks like that. Do you guys watch Luke Cage on Netflix? Because his super hard skin comes from like being genetically similar to some kind of shellfish, which I think might be an apple. You guys remember which kind of bivalve that was?
They draw their blood.
Yeah, and you can eat them and they're delicious. Wow, look at that. It's kind of suggestive. Come back here. So this is kind of an interesting data set. So what you're supposed to do here is you are supposed to predict the age of the abalone from its other features. And the age of the abalone is represented here in the rings column. So I guess they probably grow like one ring in their shell for every year. So you're supposed to look at the sex, the length, diameter, height, weight. This is you can look at the documentation on UCI if you want to know exactly what these are, but if I try to remember, this is shucked weight. You know, there are all these different weights, like weights with a shell on, weights with a shell off, and I forget exactly what their meanings are. These are just different weights. Okay, so that's the object. And should this be a regression problem or a classification problem? Because the number of rings is, I think we actually look here at the description of the data set. The highest it goes is 29.
I think it's classification, no?
Yeah, so it's a good question. So there are 29 possible categories if you want to view it as a classification problem, which is getting kind of high. You could view it as a regression problem, and really there's no right answer. I would try it both ways and see which way performs the best. But here we're going to do regression. We're going to treat it as a regression problem. And so here you can look at scatter plots of some columns in the target. And for this data, there really is a pretty, this is kind of the opposite of the concrete data set. This is a harder data set to do regression on, but there seems to be more obvious correlation between the individual columns and the target. But as we'll see, it's hard to get a high R2 score here. Okay, so now we are, okay, so now here's the question that we're supposed to be talking about. So we have to convert these letters, M, F, I, into numbers somehow. So how should we do that? The obvious thing to do is just to convert them into numbers. So M will be 0, F will be 1, and I will be 2. That's just like an arbitrary association. So it's easy, and it doesn't add any more columns, which is good because, you know, the more columns you add, the higher the potential becomes for overfitting. But the downside to doing it this way is there's not like a continuous relationship between these numbers and anything. So like linear regression is going to try to find some continuous, you know, like 0 means one thing about the number of rings and 2 means the opposite. That's what a linear relationship would look like, and then 1 would be kind of intermediate. But these are just random labels, so there's not going to be that kind of linear relationship between these numbers.
Question. But it would also depend on how much data we have, right? Because if we have, like, let's say 10,000 instances of data, then there could possibly be some relationship between 1, 2, and 3. You know, like all the zeros, all the ones, and all the twos.
Yeah. So are you talking, there's the number of rows is one thing. Oh, you're saying so there might be some relationship between these, and if we had enough data, we could discover it. But what I'm saying is,
I'm saying if there was just simply more data, like let's say, I don't know, 10,000 instances of the males, females, and the I, you possibly could draw some sort of a relationship. Like linear regression will probably draw that 1s or 2s have certain lengths, diameters, heights, or rings, etc., etc.
Yeah, that's right. We definitely do want to find some kind of relationship, and probably there is a relationship. But so all I'm saying is that if you just make up random numbers and map them onto the names, then you're not going to get like a linear relationship um, where at one extreme, when this number is low, rings are low, and then when this number is high, rings are high. There's not going to be a nice linear relationship like
Oh,
that.
I see, right.
Yeah,
Right.
because we're just assigning the numbers at random to the letters. So there's a different idea, which is, and then we see, and this is a really tough data set. This number will bounce around a lot, but the R2 score here is 0.22, which is just like not great at all. And then for some random reason, I wanted to see how polynomial features would do. So going up to degree 2 does improve things a little bit. It makes R2 go up to 0.25. But what I wanted to do now is something called, I was gonna say one hot encoding, and this kind of is one hot encoding. I'm gonna try to draw on the screen again, even though that didn't work out so well last time. Let me come back up here and click on annotate. So now oh gosh, now it's like stuck on draw. Okay. Okay, so I'm still gonna try here. So maybe you can just ignore these values. So you'll notice now that there are 2 columns and they're numerical, whereas before we had 1 column and it was one of 3 letters. So there's no, they've left out sex F here. And I just want to explain how this encoding is working and why it is what it is. So what we're doing here is exactly one of these 3 possibilities is true. It's either male, female, or immature. So the way the encoding works is you just put a 1 in the column where it's true and put zeros in the other columns. But you don't really need 3 columns, because what should I write here? What is this going to be?
1.
Exactly, it's 1 because one of the 3 possibilities has to actually be the truth. So this is saying that it's not immature and it's not male, and we know that it has to be one of the 3. So there's implicitly a 1 here because it has to be 1 in some place. So what should I write here?
0.
Yeah, 0.
0, and the next
And
one 0.
That's right. Okay. So this kind of encoding is called one hot encoding because exactly one there's 1 in exactly one of these columns and the others are 0. Some people call this practice of leaving off one redundant column dummy encoding, dummy variable encoding. I don't really care about the terminology. But the good thing about doing this is now there will be linear relationships in each column. So that, if male is 0, that will have some kind of implication for rings, and then it will go up if male is 1. So now we've thrown away our 1 column of non-linearly related data, and we've replaced it with 3 columns that do probably have some kind of, each independently probably do have some kind of linear relationship with the data. So we might expect a linear model to do better if we split it apart like this. And the downside is that we have added some extra columns. So that costs us a little bit because it adds variance. And so, error is bias plus variance plus noise. So we know that we've increased the variance a little bit, but hopefully it will pay off in a decrease in bias. I'm going to stop this. Right. So is this going to, I think these scribbles now are going to trail us forever. And what do you do about that? You have to just restart the share. Okay. All right, so how does this do? So with no polynomial features, it doesn't do much better at all. It's 22. But then if you do one hot encoding and polynomial features, then the test error goes up significantly. Sorry, the performance goes up significantly. So this is R2 score, so higher is better. And that's all. So you can see I just used the sklearn library to do the one hot encoding. You can Google it and steal the same code that I stole, but just wanted to introduce the idea of replacing numerical columns with one hot encoding. So now we know what it is. Any questions?
So professor, so the R squared basically is amount of variance explained by the.
That's right. So the best it can be is 1.
Mhm.
And it's sort of true that the worst it could be is 0. But you can actually do worse than 0 if you have a really terrible model. So models that do even worse than always just predicting the average y, you can always just predict the average y for everything, and that gives you an R score of 0. But some models will do even worse than that, and then they have negative R2 scores. So they do worse than you can do without even looking at x, which is not great.
Where did you do the one hot?
One hot?
Yeah.
What about it?
Where did you?
Oh, where did I do it?
Yeah.
Right here. So I did it using pandas. So the thing that did it was the get dummies command here.
Okay.
Um, so how does this work? So I did get dummies for the sex column. So that means create these extra columns. And then I picked the prefix sex. So that's why it's sex I, sex M here. And I said drop first equals true. So that made it throw away the redundant column.
Okay.
And so then axis equals 1. Oh, so we're concatenating. So I concatenated. So if just this part here, let me highlight slightly less. So just the part that's purple right now, that's what generated the 3 extra columns that are really 2 extra columns because we dropped the redundant one. And then this concatenates it with the entire data set. So that's why it goes in the front here. And then later we drop the sex column. And so now the sex column has been replaced with these 2 columns.
Axis equal to 1 means?
That means going along the rows. So this means that we don't want to put them on top of each other. We want to put them side by side.
Gotcha. In place equal to true, that's what?
Yeah, so I think what this means is actually modify the data frame. So if I didn't do that, then I think I would have to do df equals df.drop.
Okay.
If we have 4 possible sexes, and we still use this,
Yeah,
it would fill 3,
exactly.
and then one of them would.
Yeah, so if you have n possibilities, then you get n minus 1 extra columns.
So by adding another bias column, you do increase the variance, which causes the error to be slightly bigger, right?
Yeah, when you add columns, you increase variance, which can lead to overfitting. Then you could make we're going to learn tricks for making the variance go down again, but just adding columns increases variance. Okay, so let's go to which one were we supposed to do first? Bias and variance, the bias variance trade-off. Okay, so this one is a little bit wordy. This stuff is all on page 62 through 65 of the textbook if you want to go through it a little bit more slowly, because it is kind of math heavy. So what we do first is we're gonna sort of mathematize the idea that that error is equal to bias plus variance plus noise. And Tyler gave us a good PDF or web page about this that I put on Piazza, which you can read if you, and so it's just an alternative to the textbook presentation. But I'm going to be following the textbook here. So here we're gonna say what bias and variance are, and then show that that error sort of is bias and variance. So let me introduce some terminology here. So we're using this variable script D to represent a data set, and then in the notation we have this GD. So let me explain. Oh gosh, stop it, you freak. GD is equal to the best hypothesis that your algorithm would produce if you used data set D. So you know, if you're doing regression, maybe you get this training data, but then maybe if you do it a different time, you get you know, other training sets. I forgot that I don't know how to stop erasing. Yeah, so maybe if you do it again, then the training data looks like this. Then you do it a different time and you get this training data. You do it a different time, you get this training data. So remember, we're sort of imagining that the data is all being produced by this probability distribution that we never really get to know. We just get to sample a data set from there, which we call D. And so we get to see a certain number of examples, and these Ds are always the same length. They're like, you know, N or 20 to name a particular number. Everybody feel like they understand that? So like if these 3 points were the data set and you did regression, then GD might be this line. But if this was the training data and you're doing regression, then this would be GD. And if this were the training set and you did regression, then this might be GD. So GD is just the best hypothesis for the training data that you get. Okay, so stop this. And all right. So we have to also understand G bar. So G bar is the average best hypothesis. So if I took all of these lines that I produced over here, I could average these lines. You know, if I got many different data sets and many different lines, then I could average them all, and I would get sort of one average line. So that would be the average line that gets produced when I do this kind of regression, and that would be G bar. So expected value, you know, is just a fancy way of saying average. So this is the average best hypothesis, where the average is over all possible trading data sets. Is that okay? So once you understand G bar, everything is pretty easy. We're going to give some examples. I'm going to redo the share here so I can get rid of that crap. Okay. So this is just the definition of bias. So this is a little. Hello.
Yeah, we're here.
This is a little bit different than in Tyler's worksheet. What Tyler's document says bias squared, where we just say bias, and it's just like a different units or something. It really means the same thing. This is the way our textbook does it. So this is what bias technically is for a particular X. It's the difference between the average best hypothesis and the truth. So this is supposed to be reflective of our hypothesis space not being able to quite represent the target function. So if the target, like in an extreme case, if the target function was actually in our hypothesis space, the bias would be 0. Because if you averaged all of our best hypotheses, on average they would just be F, and this would be 0. So this is like a measure of how far the hypothesis space is from actually being able to represent F. So like if we have a linear model and F is really a degree 17 polynomial, bias is going to be high because G bar here is going to be a line. So it's going to be a lot different than this degree 17 polynomial. Okay, so this is bias as a function of a particular X. And maybe we should scoot down here.
When you said the G bar is going to be different than the 17 polynomial,
Yeah.
just elaborate more on that.
Yeah, so I'm going to try to draw here. I'll practice.
What are you trying to say is that the average hypothesis would not come close to the 17 polynomial. That's why the bias would be extremely high.
Yeah, that's right. So a degree, let me try to draw this picture. And I need to practice on my own about how to do these annotations. I just found out that I could do it at all recently, so I haven't practiced too much. But let's say that H is linear. So then G bar is just a straight line because the average of two linear functions is a linear function. So so G bar is going to be a line, and F is this thing that is just inherently more complicated than a line. It's some curvy, like degree 17 polynomial. So now for a particular X, like let's say we're considering an X right here, there's going to be a big difference between what F says and what between what F says and what G bar says. So this error will be, and then you square the difference. So we're going to end up taking the expected value of the bias over all X bars, which is kind of like integrating this area. Not exactly because of the square here. So, you know, this means that we count all of them positively. And it also, the square will exaggerate the sticks that are big. But basically, you know, one way to think of what we're doing is we're sort of taking the integral of this difference. And so that's kind of what bias will end up being when we remove the dependence from X here. It's kind of like just the area of the difference, which is going to be big if nothing like F is in the hypothesis space.
But when is F, for example, that big, like you said, 17 polynomial? Is it really that big all the time, or do we make F is what it is?
You know, it's kind of weird that, I mean, it's kind of weird that F is not more complicated than it usually is. I mean, like often in nature, you see like quadratic relationships all the time. You know, Einstein has this famous quote that nature is, what is it? Something but not malicious, subtle but not malicious. But when you discover physical laws, you know, like the law of gravitation or whatever, often the equations that govern those laws are surprisingly low degree. You know, like you rarely see anything greater than a fourth power or like a square root or something. So it's just kind of a weird property of the universe that that the laws of nature that really govern sort of the distribution of the data tend to not be extremely complicated functions, but in principle they could be. I'm going to have to redo this. It's kind of hard to sound intelligent when I'm always redoing the share. So can I do this? Okay, great. Oh, what are you guys looking at now? God only knows. I'm going to stop the share and redo.
No, we were looking at the bias.
Oh, okay. So Tyler sent us this great diagram, and maybe I'm looking at it too soon because we haven't talked about variance. But you can just look at bias. So what you know, here's the bullseye. So the bullseye is like F, and when you have high bias, this is like this G bar is sort of where your best hypotheses tend to aggregate. So here they're tightly clustered and aggregating far from the bullseye. Here they're still, the mean of these points is still far from the bullseye, right? And so what bias is in this metaphor is it's like the center or the average of these bullet holes. So if the average of the bullet holes is far from the bullseye, that's high bias. So let's talk about variance here. So variance is notice that this has nothing to do with F. This is really, before we talked about it as sort of like sensitive dependence on the training data. And that's kind of what this expression is saying too. It means that it's like the average squared distance between a training set and the average, sorry, between the best hypothesis and the average best hypothesis. So if the you know, when we did the polynomial regression with the high degree polynomials, it might be that we had quadratic data, right? So we had these high degree polynomials and they were all over the place. So if we averaged all those crazy ones, what we would actually get is something that looks like a quadratic, because the data really is quadratic. So on average, it would be doing something close to just fitting that quadratic curve. But because of the crazy dependence on the training data, there is a lot of variation from the average. So it's a whole bunch of very diverse curves that just on average seem to be quadratic. And what variance is showing is how much diversity there is in the types of curves that the model tends to produce. Okay, so back here in this picture here, variance is how loose the distribution of bullet holes is. So when the bullet holes are spread wide, so that's high variance. So here's the high variance column. So sometimes you have high variance that's sort of centered on the target, so that's high variance, low bias. Or you could have, like, here's the worst possible case, you have high variance, high bias. So the bullets are not tightly clustered, and the average is off target. And so here's the best case where you have low bias and low variance. So this picture makes them seem kind of independent of one another, and in some ways variance and bias are independent of one another. So you can come up with models that have these properties. But often in machine learning, we're considering like a family of hypotheses, like polynomials, where there's something like degree that kind of controls the complexity. And so here is model complexity. So just sort of think of this as like the number of polynomial features. So if the number of polynomial features is high, then that's high model complexity. If you have just one feature, you know, if you're in a linear model, then that's low complexity. So generally, as model complexity goes up, bias goes down. So this is from Tyler's sheet. So they say bias squared, but it's what the textbook calls bias. It's the same thing. So as the model complexity goes up, bias goes down. Let's just look back at the expression for bias and think about why that should be true. So here's the expression for bias. So as model complexity goes up, why does bias go down? It's because as model complexity goes up, there are things in the hypothesis space that are more and more like F. And so that makes like there be less difference between G bar and F. So as model complexity goes up, you get more expressive hypotheses. So eventually you can express something kind of like F, and then that makes bias go down. Let's come back down to this picture.
So how would you know how to express F? Like, let's say you were saying it was polynomial. Let's say in our case, the model complexity went up. So how would you know based on the, I guess you can say the average hypothesis, how closely you're going to be to that F? So,
right. That's an excellent question, because we know that we never get to see F, right? So in some ways you don't know, but you can kind of know. And the way you analyze the situation with your particular data set is by using something called a learning curve. And we made a couple of these at the end of the slides from last time. So these are called learning curves. So you use the learning curve to decide whether you're in a high bias or a high variance situation. So you don't get to see F, but you do get to see the learning curve. So what you do is you try different levels of complexity. Here's low complexity, degree 1. And these things slam together so that the training error and the test error slam together pretty quickly to an error value that's relatively high. That means that this is a high bias situation. So that means increasing complexity will probably help this problem. And now look, they're converging to a lower value. So it did help, and they're still converging fairly quickly. So that means that the variance is not too high. So what happens when you make it too complicated, the variance gets too high, and you get a learning curve that looks like this one. And the problem here is that the test error is not converging down to the training error because GD depends too sensitively on the training data, and you're getting like wildly different hypotheses depending on which training set you happen to get. So you can actually make these pictures for real problems because the only thing that's required to make these pictures is a big training set. You know, but now you have a certain amount of training data. Like in this particular example, I had 1,000 points. So I used 500 for training and then 500 for testing. And then I made this by only letting it train on a few of those. Like I let it train on 100 and then I see how it does. And then I let it train on 300. So that's what's making this curve.
Professor, so when you say learning curve, do you mean learning rate?
No, those are two different things.
Oh, okay.
So learning rate is how big a jump you take when you do gradient descent. But this learning curve is different. This is the tool that you use to decide whether your model has too much variance or too much bias. And usually it is one or the other. That's why they call it a trade-off. Even though they're technically logically independent, often it's a trade-off here because you're just thinking about, you know, how complicated your model should be. So as you make your model more complicated, it's going to make bias go down. So what is bias? Oh gosh, I hope I didn't close that other window. I didn't. So what does it mean for bias to go down? That makes these things slam together. No, wait, sorry. When you have high bias, they converge to an error rate that's high. So here's the high bias picture. So notice they converge to like 0.4 when there's high bias. It's because the linear model can't quite represent the quadratic target. And so you get an error, an asymptotic error rate that's high. So that's the high bias. So bias goes down as you increase the model complexity. The problem is that the variance goes up. So you actually get your best performance when there is sort of an optimal compromise between the two.
That makes perfect sense.
Good. So, and I here we're probably not going to have time to get to this, but I did the derivation from the textbook. It's also in the textbook. That's totally illegible, but let's so let's come back up here. And so I wanted to just look at this. So here we have, we've just given bias as a function of the input and variance as a function of the input. So if you average it over all inputs, this is just the average bias plus the average variance. That's what the book calls bias plus variance. So in real life, there's also noise, which is just like, you know, like instrument error and stuff like that, and weird predictions and unknown influences and things like that. So there's also in real life a noise term, and sometimes they call it irreducible error. What we're saying here is that error is bias plus variance, and all I'm saying is that's true. Error is bias plus variance plus noise, and we're just not worrying about noise right now. But let's try to figure out what this is saying. So here you have the out of sample error of GD. So GD is the hypothesis that you produce given the training set D. So if you average those over all possible training sets, this is kind of like the expected error that your algorithm is going to have. The expected error that your algorithm is going to have is going to be it's going to be bias plus variance. So this is sort of generally true. What we actually did here is mostly like the mathematics of this are for mean squared error, but it's kind of morally true in all natural error measures.
Good question, Professor. In that formula that you have here, where e.g., why wouldn't E out be the next thing? Why wouldn't that be G bar, like the average of all hypotheses and not the best hypothesis?
It's because that would require us to bring the ED inside this function, and that might just not be true. It might not be true that ED can just come inside this function like that.
I see.
If E out were a linear function, then it could, but E out might not be a linear function, in which case it can't come in. Okay, so let's look at some real examples, like how do you actually produce a G bar. So one way to get an idea of what G bar is. Now I'm just making up some data that's going to give us some pretty pictures here. So this is not of practical importance. We're just trying to understand the theory better. So what we're going to do is just make up, we're in this control situation that we invented. We make up a bunch of data sets. And then for each data set, we get some best hypothesis GI. And then we're just going to average all of those. And we're going to let that be a stand-in for G bar. Okay, and so this code does that. And I tried to make it work pretty generally. So you give it K, which is how many data sets you're going to make. And you give it N, which is the number of data points in each data set. This is the model, which is going to be like, could be linear regression or something like something else. And it's going to be from sklearn. So sklearn models all have the same interface. You just do fit and then predict. So this will work for any classifier or regressor that comes with sklearn. So maybe we can use it later to look at some other examples. And the domain is just the domain of the target function f, and the codomain is the values of the target f. So from all of those, you can produce G bar. What I actually return is this thing capital G, which is like a matrix of the G's. I think it's worthwhile to mess up the page and try to write again. So what G is a matrix, and it has kind of like G1 as the first row, and G2 is the second row, and GK is the last row. And let me just remind you what that gobbledygook means. So that is in terms of this notation right here. So these GIs are the best hypothesis that you see for each data set. So there are K data sets, and then each row is the best hypothesis for that data set. So how do you make a function a row? The columns are just the domain. So there's one column for each X in the domain of F. So that gives these G's the same domain as F does. So you can average them. So if you just literally do like NP mean axis equals 0, so axis equals 0 means go down, then it just averages all of these numbers, and what you get is G bar. Okay. I'm going to stop the share, oops, and redo the share. Okay. Okay, so here I have, this is kind of annoying. It didn't make the picture. Let's try again. This takes a while, and I might actually really regret what I just did, because K is 10,000, which takes a while on my laptop, and We only have a few minutes left in class. So it might take too long on CoCalc. Come on, CoCalc. Earn the $14.
CPU usage 94%.
Oh, where does it say that? Oh, right there. Yeah. I should have knocked this down to 1,000. I hope it. We might just be like awkwardly chatting with each other for the rest of class. So once you have G bar, the formulas for variance and bias are really simple. Okay, so here it is. Okay, so in this picture, this is for a linear hypothesis space, and the target here is this red curve, which is a cubic. It's the curve x cubed minus x, and we're doing regression. So what I'm doing here is n is equal to 10. So we're just taking 10 points at random from the domain of the red curve and then using that as a training set over and over and over again. And depending on where those 10 points are, you get a bunch of different best hypotheses. So that's sort of what this fuzz in the background is all the hypotheses that were produced for all of the 10,000 different training sets we got. And if you average all of those, the average of two lines is a line. So G bar in this linear case actually ends up being in the hypothesis space. So it's a line. So now you can kind of understand variance and bias from just this picture. So what variance is sort of the difference between the blue curve and the red curve, how dissimilar they are. Sorry, that's bias. Bias is the difference in the red curve and the blue curve. Variance is the diversity in these G's. So this is like actually pretty kind of tightly, all of these hypotheses are fairly similar. This is like not bad variance because no matter what the training set was, we got a line that pretty much similar to the blue line. So the similarity of the fuzz to the blue line is the variance. So let's look at, yeah, Yuri?
Yeah, that was my question.
Okay. And now we have, I think this is a quadratic. Yeah, this is a quadratic model. So it's kind of funny here, like sometimes this model will produce an upward facing quadratic and sometimes it will produce a downward facing quadratic depending on the training data. But when you average it, it still averages out to a line, which is kind of funny that G bar is a line when the hypothesis space is all parabolas. So here again, the bias is the difference between the red and the blue curve. And the variance is how different the fuzz is from the blue curve. And so now I do degree 7, and it produces kind of a crazy picture because these things are going off really high. So now there's the red curve is there. So what we would see if we could look at this, actually I made a picture of it down here. So what you notice that there's this cubic curve here. So what that is F, and it's also G bar for degree 7. So G bar for degree 7 is actually indistinguishable from the target. So that means what? Bias is?
Bias is high.
Bias is 0 here because F and the degree 7 G bar are actually the same. So that's a 0 bias situation. But it's kind of high variance because you can see that the fuzz is kind of all over the place. So that's the difference between the family of best hypotheses and the average. So you can actually compute these things and get real numbers because we made up all the details. So here's the bias variance breakdown for the degree 1 model. So bias is 403 and variance is 122. And then you take their sum to get the expected error. And it turns out to be 526. So here's the degree 7 model. So the bias has gone down to almost 0. And that's because you can't tell the difference between G bar and F for the degree 7 model. But the variance has gone up to be 1342. And then when you take the sum of these, you get an expected error that's higher. So which model is better for this data in this situation? Would you rather have the degree 1 or degree 7?
Degree 1, I think.
Yeah, degree 1, because the expected error is lower. 526 is lower than 1342.
Even though the bias is really low in the other model.
Yeah, yeah. So we got a big improvement in bias, but we also got a big increase in variance. Okay, great. So that's all I had to say. There's this really technical derivation from the book that you can look at if you want to, that just shows how to prove it. So here's the expected out of sample error, and then you can go through the derivation if you want to. So let me take attendance really fast, and I'll see after that. We won't meet on Tuesday, and I'll see everybody in a week next Thursday. Okay, Usam, I better go. I better stop this so I can see people's names. I have to stop now because I was doing recording and it has to encode on my machine, and there's just enough time to do that before I have to start my next class. So I'm going to count everybody as present, and I'm looking at people here, and I'm instantly memorizing who's here, so I know, and I appreciate you coming, and I'll see everybody in a week.
Thank you.
Thank you, Professor.
Bye.
Thank you.
Thank you.
Thank you.
Bye.
Thank you very much.
Thank you, Professor.
Bye.
Also, Professor, I have you on Piazza.
You sent me a message on Piazza? Okay. I'll get back to you. I have to teach my other class, but I'll get back soon.
Okay, cool.
Okay. All right. All right. And El Haji, will you write me back over email, and we'll find a time to meet soon. I'm sorry that I can't do it right after class, but we'll do it soon.
All right, no problem. Thank you so much.
Okay. You're welcome. Bye.